Okay, in this video we are continuing to talk about acceleration. So just like velocity, acceleration is a vector quantity. There's our old friend Vector from Despicable Me. And as he said in his introduction, a vector has both magnitude and direction. So we need to describe, when talking about acceleration, how big is it in terms of the number as well as the direction. And for now, when we're talking about one-dimensional motion, that can pretty much be accomplished with the negative sign or the lack of a negative sign. So a positive acceleration, if we set up our x and y axis, and really we're only concerned about the x axis for now, positive x is to the right, and negative x would be to the left. So if we're talking about a positive acceleration, it is accelerating to the right. It is increasing the velocity to the right. And if it's accelerating to the left, that's going to be a negative acceleration. So a quick little clarification here. There is a difference between negative acceleration and deceleration. So if we are accelerating to the left, if we've set up our x-axis coordinate system and we're traveling to the left and we are accelerating in that direction and going faster and faster and faster, we have a negative acceleration. But if we're going faster and faster and faster, we're not decelerating. Deceleration occurs when the acceleration vector is opposite in direction to the velocity vector. So if we're traveling to the right, we have a positive velocity in that direction, and we accelerate to the left, we are going to be decelerating. The two vectors have an opposite direction. Eventually, it will decelerate to 0, and then unless that acceleration is changed, then it will start to accelerate in the negative direction. And the same thing can happen in the opposite direction. If we have a negative velocity but a positive acceleration to the right, those two are opposing each other. The negative velocity is going to begin to decelerate because of this positive acceleration applied to the negative velocity. So basically, deceleration has to do with not whether it's going to the right or to the left, but how is its direction related to the velocity, whereas negative acceleration is all about reference to the coordinate system. So if we're going to the left here, that's a negative acceleration, and that's positive acceleration to the right. Just like with velocity, we are, for the most part, going to be talking about average velocity. So if we have an A with a bar over it, we're talking about average velocity. That's equal to the change in velocity divided by the change in time. But if we wanted to know the instantaneous velocity, that would be what happens when this time variable here, rather than being a long period of time, is shortened to a very, very, very small period of time. The limit as delta t approaches 0. So imagine that this is just the tiniest fraction of a second, and we measured what the change in velocity was over that very small period of time. That would give us the instantaneous velocity. Now, there are frequently situations in which acceleration will be constant. So, as it happens, there are a variety of formulas that we can use, and these are our first 4 big formulas that you're going to need to know. I have summarized many of the formulas used throughout the class on a formula sheet that I've posted to Blackboard, but these are perhaps, at least early on here in the semester, the 4 most important. I'm just going to refer to these as these 4 constant acceleration equations. And so think of these as tools in your toolbox. These can be used to solve problems, okay, but you need to use the right one. You need to use the appropriate tool for the appropriate job. So you're going to have to maybe do a little bit of trial and error, or think about it a little bit, looking at the variables given to you in a problem and the variables that appear in these equations. Which of them is going to be the most helpful? So I tend to think that just jumping in and doing an example is the best way to learn something. So let's look at example 2.7 from the textbook. You are designing an airport for small planes. One kind of plane that is going to be using your airport has to reach a takeoff speed of at least 27.8 meters per second before it can take off. If it doesn't achieve that velocity, it will not take off. And it is capable of accelerating at a rate of 2 meters per second squared, 2.00 meters per second squared. If our runway is 150 meters long, will the airplane, assuming it starts from rest, be able to reach its required takeoff speed, accelerating at 2 meters per second down a 150 meter long runway? And if not, what is the minimum length that we need? So let's recap what we know. We know the airplane is going to start from rest. So the velocity 1 is, actually, let's take a step back here to look at these variables. So let's take a look at the subscripts in particular, is what I wanted to bring to your attention. So up until now, we've been using 1 and 2 for instance, for x position. x1 is initial position, x2 is final position. We're going to transition now to, instead of using a subscript of 1 and 2, we're going to start to use a subscript of 0 or not, and no subscript. So for instance, in this formula here, velocity with no subscript is the final velocity, and velocity with a 0 or not subscript is the initial. So what this equation is saying is that the final velocity is equal to the initial velocity plus acceleration times time. Here we have final position equals the initial position plus the initial velocity times time plus 1/2 at squared, and so on and so forth. Final velocity squared equals initial velocity squared plus 2 times acceleration times final position minus initial position, and the average velocity is equal to the final velocity plus the initial velocity divided by 2. Okay, so instead of using 1s and 2s, we're going to start using 0s and nothing. Okay, so really what I want to say is my initial velocity, so I should use a 0. So V naught is 0 meters per second. Plane's going to start from a standstill, and then it will, well, we don't know for sure. We want it to have a final velocity of, what was it, of 27.8. That's what it needs to be, but will it be? Will it be able to achieve that velocity given the other parameters? Let's find out. Delta x equals x2 minus, no, I shouldn't say x2 minus x1, x minus x naught, and that is 150 meters. That's the length of our runway. And the other thing we know is how fast the plane can accelerate. It can accelerate at 2 meters per second squared. So that's our acceleration. Acceleration is 2.00 meters per second squared. So we've got v, we've got v naught, we've got x naught, and we've got a. What we need to do is we need to look at these 4 equations and figure out which of them is going to work for us. The easiest way, I think, to do this is to first recognize that we don't know t. T is not given. We don't know how long it's going to take to go down the runway. So if we have an equation here with a variable that we don't know, and we're not asked to calculate, it's probably not going to be the one for us. So we probably don't want this one, probably don't want this one. This one isn't really very helpful. This is basically just telling us average velocity is the first and last divided by 2. This is the one we're going to want to use because we know the final velocity, or at least what we want it to be. We'd like to calculate what that's going to be. We know what the initial velocity is. We know what the acceleration is, and we know what the length of the runway is, x minus x naught. So we've got everything we need for this equation. That's going to help us solve this problem. So we write out the equation. The final velocity squared is equal to the initial velocity squared plus 2a times x minus x naught. So the velocity is going to be equal to the square root of everything that's here on the right side. So the initial velocity, that's 0. Plus 2 times the acceleration was 2.00 meters per second squared, times the length of our runway was 150 meters. Okay, so this is going to be equal to 2 times 150 is 600. So this is the square root of 600. Let's see, our units there would be meters times meters is meter squared. Whoops, let's undo that. Okay, meters per second squared. And when we take the square root of these, we'll take the square root of the meter squared and second squared and just end up with meters per second. So the square root of 600 is 24.5. 24.5 meters per second is the final velocity that our plane will achieve. But our problem statement said it needed to be 27.8. So this is less than 27.8 meters per second. So we got a problem here. Our plane is not going to take off. We need a longer runway. So how long does it need to be? Well, we can actually use that same equation. Velocity squared equals the initial velocity plus 2 times acceleration multiplied by the change in position. Okay, and this time we'll leave this as the unknown, the length of our runway, and instead plug in the final velocity that we desire. Okay. Now, the way the textbook tends to solve these problems, if you're following along with example problems in the textbook, is to rearrange all the variables first before plugging in the actual numerical values. I understand why they do that, but it can be a little easier for some students, I think, to just plug in the numbers first. So why don't we do that? We want 27.8 meters per second. And then we have to remember to square that. Don't forget the exponent. That's a real easy mistake to make. Equals, our initial velocity is 0, plus 2 times the acceleration is 2.00 meters per second squared, times, I'm just going to call this x minus x naught. I'm just going to call it delta x, change in x. So if I then solve it algebraically,